Hi, everybody. Welcome to the Routing Protocols in Industrial IoT webinar. This is Nalini Elkins of Industry Network Technology Council, and this webinar is being recorded. Please let me know if you have problems with sound or anything else. You can use the questions button or chat button to let us know. This webinar is being presented by Pascal Thubert. This is a part of our multi-year IPv6 deployment project at enterprises, where we provide training, analysis, and help you plan your deployment. The reason we're doing IoT is that we feel that the scalability of IoT will depend on IPv6, and thus it's very important to cover the whole IoT area within our perspective. This series is being made possible by a grant from ISIF Asia to the India Internet Engineering Society, and INTC. This organization is a partner of IETF. We work together, and we have done so for a few years to bring you all these webinars. Thank you so much to the support from ISIF Asia, and of course, Aaron in the past. So just a couple of things about myself. I'm the president of INTC. We are a nonprofit, and we encourage all of you to become members and give us your feedback as to what is in the best interest of enterprises going forth. That is the focus of this organization as far as the standards world. Pascal, now, this is the interesting part. He has written many of written or co-authored many of the base RFCs around which we do IoT these days, and it's really a great honor to have him presenting with us and working with us. So on that note, I will give him the presentation, and let's go. Okay, Pascal, you're on.
Okay, Nalini, let me share my screen, and hopefully that's the right one that's going to be shared.
Yep, we see the webinar.
We see the webinar full screen, right?
Yes, yes, we see it.
Okay, so thanks so much, Nalini, for the introduction. And yes, this is the IoT Track webinar. That is a series of webinars being presented by a number of people that you can see on the screen. So thank you all for attending, and welcome to this one session, which is the fourth session in the series, dealing with mostly RPL, the routing protocol for low power lossy networks, the base RFC, and then the continuation work that has happened since then. We have only 1 hour, so I'll be quick. I'll be skimming through slides. I wanted to share some ideas with you on many of the slides, so that's why I kept them. But I won't be able to spend as much time as those slides would deserve. So please download the material and visit it by yourself. And you may drop me emails if you have questions. So what is different, and why did we need a new routing protocol for low power lossy networks and for the IoT? The first thing is we needed to scale to thousands of devices in a subnetwork. And this is not something which is usual to classical routing protocols, which have the scalability limits, which are in the order of tens or hundreds, and certainly not tens of thousands as we need in some large IoT networks. We need to deal with radios, number of radios, and the routing protocols, apart from what's done in MANET, are usually not well defined, or don't have a good understanding of radios. And radio is necessary in the IoT because that's how you can scale. If you had to wire thousands of devices, you would not be able to. So the only way to connect all those devices is effectively to have radio interfaces, and over a radio interface, a device might see many other devices. Same goes for addressing with the limits of a /24 subnet in before, you could not reach the thousands that we need. And then there is this additional problem that the network can become very dense. And as the network can be very dense, you have to think about local transmission, short range, and allowing, I'll come back to that, but allowing A to talk to B while C talks to D at a distance, which means spatial reuse and routing. Routing is the thing that will allow A to talk to B at the same time as B talks to C talks to D, without having a single broadcast domain where C could not talk to D because it would interfere with A talking to B. So routing is a key element for the scalability in a dense network. Now, a second problem we had to deal with is dynamic topologies. Classically, when you do a routing protocol like SPF-based or SPF or ISIS or LSR, you expect that the topology will be stable, because each time something changes in the topology, you have to reconverge, as they say. And that basically cannot, we cannot live with a constraint like this in a network with thousands of nodes and many of the links flapping at some given points of time. Basically, the whole point of converging becomes impossible. And the point that you need in link state routing protocols, where you need to know every link, every node, the state of everything, that doesn't scale. You cannot grow and live with dynamic topologies in that world. So guess what? When you have radio links, you can't expect that a link will be stable and will survive for a while. The whole routing topology will continuously evolve. And so you need a routing protocol that can adapt to a continuously evolving topology, and we'll see how Ripple does that. Like I said, we have possibly hundreds of devices now in our range. And you can't start establishing routes via all those 100 neighbors to all the possible destinations in the world. Part of the game is to select who you're going to talk to reach the rest of the world. And that's an interesting concept, because you don't know before you talk to the neighbors where they can reach. And at the same time, you can't talk to all your neighbors to see the rest of the world. So how can you build a network that will allow you to reach everybody, and yet not get routing updates from every damn neighbor, the hundreds of possible neighbors that you may have? And we'll see that there are methods in Ripple to select the neighbors and then to dampen the control exchanges that you have with those neighbors. And then a key thing that everybody knows about IoT is most of the devices are very constrained, meaning that we cannot live with a lot of state in the constrained memory of the devices. We cannot demand too much CPU for the computation of the route. And because the radio itself is constrained, I mean, the spectrum that we're going to use and the energy that we can place in the air is constrained, we also need to minimize the control plane. We basically had this requirement for Ripple that we would not use more traffic for control than there would be for data. And you'll find that this has a consequence on how we control the state, and mostly how we repair. Ripple will build the routes proactively because you need to ping, but then it will only fix lazily or reactively, meaning that if a route is not being used and it happens to be broken, we won't fix it immediately. Then the quality of the link itself compared to wire is fuzzy. Sometimes the link has a good throughput, and the next second there is an object in the Fresnel zone that passes, or because something moved in the environment, the reflection will cause multi-path interference, which will be there for a split second, and then something else changes and the problem goes away. So the quality of the link is non-deterministic. The expectation that you can have on any given hop will change all the time. Ripple has to live with this. And we'll see that to cope with that, Ripple builds not routing trees, but directed acyclic graphs. And so these are the basic requirements that we have to live with for Ripple. Now, let's go through a number of concepts and see how we can position Ripple and why we actually used a certain variation of those concepts to build Ripple, why we made those decisions we made. First thing first, I already introduced it, but using Ripple in the first place, using a routing protocol in the first place, is for spatial reuse. If we want in this picture A to talk to F directly, it means that A will have to use a lot of energy and a very large transmission range. And you see in this picture the interference range, the range at which this transmission would interfere, is even larger than the transmission and actually grows faster than the transmission range. So the more energy you put in your radio, the faster the interference range will grow around your transmission, meaning that in that interference range, there cannot be another transmission. And so routing enables you to use a very short range transmission, very low power, very low degree of interference, but then you cannot go as far. A can only talk to B, and but at the same time, D can talk to E without interfering with A. There is enough power difference between the transmission that B will receive transmission for A. So basically, the whole game here is to do more hops, but with less power, which diminishes a lot the interference that are present overall in the domain. Second concept is centralized versus distributed. There are basically two camps here. One camp is the centralized camp is what you've come to know as SDN, basically software-defined networking, is when you have a controller somewhere, an intelligent device that sees all the links and sees all the devices, basically the whole routing graph. And for each flow, it will decide which path the flow will take. So that basically allows a global optimization of everything you're seeing with a God's view. But on the other hand, it consumes a lot of resources on the network to install every path. And it's not highly resilient to a lot of changes, because each time topology changes, as I said earlier, you have to go back to the controller and see how that impacts all the flows. And possibly if you have to move a flow because the link is down, then you have to push back on another flow, etc. This creates a cascade effect. So in a centralized world, building the whole routing based on centralized doesn't scale and doesn't live with the radio quality that we have. So Ripple-based basically is a distributed routing protocol. Now, once you've done that, there is the new work in DAO projection that I will talk to you about a bit later, where we add some optimized path to the Ripple routes so as to get the best of both worlds. Base Ripple distributed to allow connectivity, but not necessarily shortest path or something, and then some centralized DAO projection routes, which will be additional overlays to optimize for particular A to B. So Ripple, very soon, because DAO projection is nearing last call at the IETF, Ripple will have both modes. Now there is another game, which is proactive versus reactive. Proactive is when you install all the routes first, all the state that you're going to need for routing, and then as a second step, you effectively forward packet, and when the packet comes in, you have the state that you need to forward. The classical routing protocol, SPF or SR, RIP, ISIS, EGRP, BGP, whatever, Babel, they are all proactive. Now, in the MANE space, there are a number of reactive proposals or reactive RFCs like load, AODV, DSR. And we have two Ripple extension, P2P Ripple, which was an experimental RFC, and AODV Ripple, which is nearing the state of RFC. which extend Ripple to do a reactive method. So if you look at the whole spectrum, if you like, of Ripple capabilities, the main Ripple is the most classical distributed type of protocol, proactive, etc. At one extreme on its side, you will have AODV for really optimized stuff, completely controlled by a controller. And on the other extreme, you will have AODV Ripple, which will be fully distributed, fully on demand. So basically, Ripple, AODV Ripple will only install the routes when you need them. So Ripple will only know the routes that are needed and not the ones that are not. But then when you have a new packet for a route that does not exist, you will have to form the route before you can effectively transmit the packet. If you look at it in the classical world, ARP and IPv6 neighbor discovery are reactive. When the router doesn't have the destination in his neighbor cache or in his ARP cache, it will have to broadcast a lookup. Hey guy, give me your MAC, I have your IP, but I'm missing your MAC. And ARP and ND will reply to that. But it means a broadcast over the network. Now, a reactive routing protocol means a broadcast of broadcast of broadcast. You have basically to shout across the multi-hop network to find where your destination is, and only when the reply comes in, now you know how to get there. So Ripple is mostly proactive, but it has a variation which is reactive and a variation which is centralized and optimized. So that basically is a control plane problem. The related issue is whether you want to install a state, typically proactively, in every router, so every router has a state to go to a destination, or if only the source of the packet knows how to get there, in which case it will have to write all the individual steps in the packet header so the intermediate routers know what to do. So stateful refers to, again, classical routing protocols where every node has a state, a routing state, a routing table, and source routing refers to the mode where the source of the packet will install what we call a source routing header in every packet so they can be forwarded to destination. And Ripple needs both. Ripple has what we call storing mode, where there will be some amount of state in every node. And we'll see it's not the optimized path to everybody. It's just a limited amount of state. And it has the non-storing mode where only the root has all the state. And that means that the packets will flow always to the root using a default route first if the packet is generated inside the graph, inside the Ripple domain. The only route that exists in the Ripple domain is a default route toward the root. And when the root gets the packet, then it can add the source route header, and the packet can go down. So stateful corresponds to storing mode, and stateless corresponds to non-storing mode. Another big concept in routing is link state versus distance vector. Link state basically says, oh, I know the whole topology, I know all the links, I know all the nodes, so I can compute the shortest path between me and the destination. And guess what? Every node along the path doing the same computation will find that the rest of the way is congruent with what I had computed. So it only works if my view of the network is exactly the same as the view of all the next hop. Otherwise, there is a risk of a loop. And effectively, when the network is unstable, link state protocol create what we call micro loops, local loops, before everybody converges to the new state. That was unacceptable in a radio network where the links flap all the time and there are so many links that you're sure that on your path something will break at some point of time. So basically link state was very rapidly eliminated from the scope of Ripple, and we went for distance vector. With distance vector, you don't need to know the whole topology. That's a big advantage. You just need to know which next step will give you the best path to a destination. So that's one big thing. So a lot less state in the devices. The way actually Ripple will use distance vector will avoid the need to know all the destinations. Ripple will basically build a distance vector graph all the way to the root. And cherry on the cake with distance vector, you can use any next stop which is shorter than you are to destination. So instead of building a routing tree, which is typical to shortest path, you can have a directed acyclic graph, and we'll see that it's very useful when the links are flapping and you need multiple solutions. We'll come back to that. Finally, route stretch versus shortest path. There is a tension in the routing world between having an optimized path from any A to any B and the amount of control traffic that you're going to spend, and the amount of memory and topology awareness that you need to have. The best the path, the more topology awareness and the more sensitive to change you are. So basically, Ripple is probably it is the only IETF routing protocol that has what we call a route stretch, which means a balance between the shortest path and the cost. To allow for much lower overhead in the routing, Ripple will not guarantee any to any shortest path. The only shortest path that will be obtained is between the nodes and the root and back, because most of the IoT traffic goes from the sensors towards the root, or from the root towards the sensors. And the root is basically the access to the internet or something. And if you consider that the way Ripple does it, it was the first IETF protocol to do this sort of thing. Now there is Rift. Ripple is anisotropic, meaning that its behavior depends on which direction. So basically, we'll see that there is a DAO procedure which starts from the root and spreads. So it's directed away from the root, and it builds a default route towards the root. And then there is a second wave which comes back the other way towards the root, which will install the path from the root to the destination. So it's anisotropic, and it's actually circular anisotropic, meaning that it starts from one point and spread, and then comes back as a return wave towards that point. And what you do away from the root is very different from what you do towards the root. In particular, a next stop selection happens only in the first phase. So now other concepts, routing trees. I mean, like I said earlier, the link state protocols typically will build routing trees. And that's very useful, for instance, for multicast. And the issue with this is if you have a breakage or link flapping, if you have only a routing tree, for instance, in the red tree here from any node to the root, if you have only one routed tree, if a hop goes down, then you cannot connect back to the root. So in order to maintain a tree for things like multicast, Ripple has a tree inside its structure. It's called the preferred parent tree. But the forwarding of packets doesn't need to follow the preferred parent tree. It can follow a more generic directed acyclic graph. So a directed acyclic graph can be seen as, say, an augmentation of a tree where other hops are usable. The links are directed. And actually, what Ripple builds is direction-oriented directed acyclic graph, meaning that if you follow the arrows, you will always reach the node, which is the root. A more generic DAG could have multiple destinations. So when you follow the arrows, you would reach one of the destinations. But with Ripple, we effectively build separate directed acyclic graphs like the green and the red, even for the same instance, as we call it, rather than having a directed acyclic graph which would have multiple destinations. So all the nodes inside the same DAG will have the same root. That makes things a lot easier. Sub-DAGs and fan-out DAGs. So the sub-DAG is basically everybody who's behind you. So for instance, you see in the green DAG, A has a sub-DAG, which is all the children that may send traffic via A towards the root. So it's A sub-DAG. It's all the guys. If A dies, basically they might be impacted. Now the fan-out DAG is following the DAG is what you can reach. So it's the opposite of the sub-DAG. It's all the nodes that you might use for your data traffic. And in this example with node B in the red DAG, the red fan-out DAG is all the possible path. It's the aggregation of all the possible paths for packets from B. Depending on which link works well, the nodes may forward on one of the forwarding solutions that they have, what we call feasible successors in the hierarchy. And this takes us to RPL. Now that we have seen the design consideration that we used for RPL, let's see what we did. So first thing first is we need a little bit of terminology. So as I said, RPL builds direct acyclic graph, which are oriented towards a route. The route typically connects to the internet, gets traffic from the internet, and sends traffic back from the devices towards the internet. So the direct acyclic graph connects the children to their parents. And since it's a DAG, a child can have more than one parent as opposed to a tree. Now, there can be a non-LLN backbone which connects the route. For instance, the blue backbone here connects the routes which are in green in this picture and qualified. The routes are qualified of a rank 1. And as you go deeper into the network, the rank will augment. And the rank characterizes the distance. So here it looks like a hop count, but really on the radio network, it is never a hop count. Because if you wanted to minimize the hops, you probably use links with a very bad quality and get a result which is really not what you want. Each RPL forms multiple instances, and the instances can comprise more than one DAG, basically interconnected via their route over a backbone. Now let's see how it works in a little bit more detail. Say we have this radio connectivity that I represented here. What's going to happen is, as I said, there will be two phases. The first phase, which we call DIO, will create the default route towards the cluster head, which is the root. And the second phase, the DAO phase, comes back from the devices towards the root. And depending on the mode, storing mode, non-storing mode, the second phase will be a hop by hop, or it will be directly to the root. So the way the DIO will work is, it's basically the distance vector type of operation. A message is sent by the root, and the nodes which receive it with enough quality will say, hey, I'm a child of the root. I'm depth 1. And then again, the depth is not really the metric that we're going to use, but it's for the sake of the explanation here. And then they will re-forward the DIO. And the nodes which see that that forward the DIO propagated, as we say, because we change it a little bit, but some information remains the same. As the DIO gets propagated down, the rank, which really characterizes the distance, augments. And the nodes select the number of parents with a rank that is that has to be smaller than theirs, right? The parents are nearer to the root, but you basically want to have enough of those parents. So there is a tension between the rank that you select for yourself and the number of parents that you want. And typically, if you're greedy and you want to have many parents, you will have to pick a rank which is very bad, and then nobody will want to attach to you. So that's why we call it a greedy behavior. And basically, RPL wants to avoid that type of greedy behavior. So what we say is you have to look at the best parent that you may have, and that limits the number of the other parents. Basically, the step of rank, the cost to go to him, limits what other parents, what additional parents you may use, because you will compute your own rank based on the cost between you and that best parent, that preferred parent, and only the nodes which are somewhere in between are usable as feasible successors. With this, we avoid basically the greediness problem that I discussed earlier. So this is all self-forming, self-healing. Each time there is a change in the graph, we'll recompute this DAG, or we'll locally heal it if we can locally heal it. And the second phase now, the DAO, goes from the devices, spreads back towards the root, and like I said, depending on the mode, it will establish a state all along its path towards the root. So, or in the fan-out DAG that we discussed earlier, or it will just tell the root, That's where I am. I'm this node on the left, and my parents, my potential parents, are this guy and this guy. That's the second mode is called non-storing, because you don't store any state in the intermediate nodes. Now, when you are in this non-storing mode, because each edge basically has been indicated to the root, the root can reform the whole graph in its memory and decide what path to use to go to a destination. Based on that, it will form a source route, a header, and it will forward to the devices. Okay, so more details in storing mode. Like I said, you basically in storing mode, the DIO is the same as in non-storing mode. You basically build a default route towards the root, but you send your DAO up by hop all the way to the root, and every node on the way between you and the root will remember that you're coming from that direction. And so basically, when 52 says, I'm here with a DAO, 42 will remember, oh, 52 is just attached to me. 32 will remember that 52 is via 42. 22 will remember that 52 is via 32. 11 will remember that 52 is via 22, etc. All the nodes remember which leaf, which terminal node is, and all the hops in between are in its sub-DAGs. Every node maintains the state of its sub-DAG. The cool thing is when 51 wants to send a packet to 52, basically it will build the packet such a way that you have what we call an RPI. I will come back to that, but it's some useful information for RPL that we place in every packet, and then the data. And when the packet is forwarded, initially it's along the default route towards the root, because 52 is not known by 41 and 31. That's the route stretch that we are talking about, because 52 is only known by the chain of parents in its fan-out DAG. 31 and 41 are not in the fan-out DAG, because 52 can never send a packet to the root, which will go via 41 or 31. So the DAO did not pass through them. They are not aware of the existence of 52. That's how we save a lot of state in RPL. So the packet initially goes along the default route, but when it reached 22, 22 is in the path of the DAO. So it is in the fan-out DAG of 52. So 22 has a state for 52, so it can now forward the packet along that state. And guess what? Every node along that path is effectively the node that forwarded information about 52. So they all know about 52, and the packet can go down all the way to 52. So you see in storing mode, there is a stretch when you go from a leaf to another leaf. And the stretch is you go up towards the root until you meet a common parent. And since a parent knows all his children, grandchildren, etc., then the common parent will know how to route to 52. When a packet comes from the internet, so basically a packet source X in the internet, destination 56, this node on the bottom right of my drawing, since we need this RPL information that I mentioned about, we will have to tunnel the packet to insert the header that we call an RPI. It's an IPv6 extension header. It's a hop-by-hop header. And to insert it, the root will have to basically tunnel the packet. It may tunnel the packet to 46, which is the parent of the destination, or to 56, which is the destination. You tunnel to 46 if 56 is not aware of RPL. So if you have a leaf which is RPL unaware, we call that a RPL unaware leaf, then effectively the knowledge about 56 has been injected in RPL by 46. And so the root will tunnel to 46, 46 will remove the tunnel and distribute to 56, which is directly attached. Now, if 56 was a router which is aware of RPL, etc., then the root could tunnel all the way to 56, 56 receives the packet, decapsulates, looks at the inner O and the destination, passes to up the stack. So basically the overhead of RPL appears when you have a packet that is coming from the internet because you need to add the RPI. But as we saw on the previous slide, when the packet is generated within the RPL domain, a RPL aware node will effectively put the hop-by-hop header in its packets there will not be an encapsulation. So the extra cost will just be the RPI, not the encapsulation. Now, when we do storing mode, non-storing mode, I'm sorry. When we do non-storing mode, it's a bit different. It's a bit different because, like I said, the DAOs are sent to the root directly. Each DAO will say, I'm, for instance, 41, and my parent is 31. 31 will send a DAO say, I'm 31, my parent is 22, etc., etc. So basically, the root has all the vertices. Now, the only state that exists in the node is the default route. How do I get to the root? So when 51 sends a packet to 52, now this packet will have to go all the way to the root. And when the root forwards the packet to 52, it will go through its table of all those vertices, resolve a path which works for 52, and it will have to tunnel to inject all the hops. And you see the overhead is a lot more than before because now you have to say via 11, via 22, via 32, via 42. So this is a source route header, which is the ripple variation of the RH0. So RH0 in IPv6 has its problems. It could be used for attacks, etc. So there are limitations in what you can do with RH3, which is the ripple routing header, and basically it's lawful to use an RH3 as long as basically the constraints are respected, and then you avoid the attacks that I discussed about. But still, the packet size is a lot more than it was before. So that's basically the overhead that you can get in non-storing mode. Okay, so second concept of ripple. Ripple has multiple instances. Why do we have multiple instances? Because depending on what you want to do, you might want to use different sort of metrics. Radios can have many different metrics when you build a radio network. Or you might want your packets to go out to exit your network from a different gateway. For instance, if you have a gateway which is provided by your power utility to control your washing machine, etc., basically the utility wants to start and stop some IoT devices in your home, then you basically want your washing machine to belong to a ripple network where the root is the meter or something that the utility has installed in your home. At the same time, you might want some other IoT devices like your front door or something to be connected to the internet using your normal home gateway provided by your service provider, for instance. So these are two different networks. When you place a packet along the default route, you need to say, oh, I want, this is an IoT packet for my power utility. Let me place it in the DAG that gets to the utility meter. So basically what's going to happen in that case is the utility meter will be the root of one ripple instance, and the normal home gateway would be the root of another ripple instance. And just by selecting a routing instance, you will basically make it so that following the default route, you get to the proper gateway. So if the washing machine knows that it needs to use ripple instance 5, which is the one that goes to the meter, then we're all set, basically. And like I said, another reason is if you want your instances to operate on different metrics, like one is optimized for reliability, another one is optimized for minimizing the hops, another one is optimized for throughput, then basically the metric you're going to use to build your ripple network will be different. And that's how ripple is extensible. The main RFC 6550 describes a core distance vector functionality with an abstract metric, an abstract scalar metric called a rank. But effectively, how you compute that scalar metric is done by something that is akin to a plugin in a web browser that we call an objective function. For each instance, we will say, hey, it's this objective function. And the objective function understands the number of metrics that are distributed by ripple or obtained for one hop from the radio network itself, from your radio interface. And it will compute the rank and the additional cost, basically the additional rank, the step of rank, as we call it, between a node and the feasible parents. So Each instance can have a different objective function. There can be many objective functions. The AETF has standardized at least 2 of them. But then if you have a new use case, you may use your own objective function and define how you will compute the rank based on what you want to optimize. And that's basically what I'm saying in this slide. So the key is we call this external function, if you like, to compute the rank increment based on metrics that we gather from the environment. But also, since it's not just a polynomial function of the metrics, but it can also be constraint, test, logics. So the OF has metrics and it has logic. And by coupling that logic, which can, for instance, implement policies and constraints, you can effectively decide a parent that is feasible because it's okay to talk to him, and because the metrics are good when you send the packets to via him to get to the root. Another key thing in RPL is the use of trickle. Trickle is its own RFC, but basically what it says is when conditions are stable, when you're saying something or repeating something that your neighbor are also saying, then basically the chances that it is of interest is going down and down. And so the period at which it should be said also needs to go down and down. So basically, you're listening to the environment for a certain period, which is this I that you can see on this picture. And for the first half of I, you count how many neighbors say something. And if what you want to say is the same as what those neighbors say, and you realize that enough neighbors have already said it in the first half, then basically you will not repeat it. Effectively, the way it really works, because we have to introduce a random here, is that in the second half, we will start a random timer, which will kick somewhere in the second half. And we'll count everything which was heard in the first half plus in the timeout period of the second half. And what that is more than a certain constant, then we say, hey, it was said enough. So my neighbors should have heard it because I heard it so many times. So let me not say it as well. And that's how we get a relatively low amount of broadcast, for instance, for the DIOs, even if the density of nodes is very high. Because most of the nodes will hear that what they wanted to say was already said. So they will refrain from saying it as well. Very important component to RPL. And then RPL has all those metrics which are standardized, but then won't go through that. But basically, that's a great many metrics that you can use, and then you can always extend with your own. Okay, so as I hinted earlier, within the same RPL instance, you might have, for instance, 2 home gateways that you connect with a wired LAN. And you don't care which gateway is reached by the IoT device. And so what you're going to do in that case is you're going to build 2 instances, each gateway being the root of one of those instances. And now, if one of the root dies, then the nodes can always fall back to the second DAG of the same instance. They just select the shortest path, like the best parents, to the best route. And they will use that one. So basically the nodes will naturally spread their traffic. They will attach to different DAGs, and so the traffic will be distributed this way. Now, obviously, if you have a very large network, and we build network with thousands and thousands of nodes in the smart grid area, there needs to be a little bit more than magic to really balance well. Obviously, if you positioned optimally the different possible routes, then yes, the load should be balanced, but it's very hard to do. So in the real world, you probably need some logic, some external controller to observe the network and decide, how you effectively balance the things. Otherwise, you have risk of oscillation and stuff like that. Now, like I said, there can be multiple instances, and a node can belong to multiple instances. So if, for instance, in my example, the power meter is on one side of the house and the home gateway for normal internet traffic is on the other side, all the nodes in the middle may be programmed to belong to both instances, so they can relay packets towards either gateway depending on which instance the packet has been placed. And remember, I told you there is this hop by hop header, the ripple packet information, the RPI. Well, one of the things that this guide contains is effectively the topology indication, which says which DAG, which instance really, which instance this packet has been placed on. Okay, so that was a very, very fast summary of why we built Ripple the way we built it and what we built. Key things to memorize: it is an anisotropic routing protocol. It operates differently for going towards the root and going back towards the node. Going back towards the node is following routes which are installed by DAO messages. And the DAO messages can be storing mode or non-storing mode. In storing mode, they are forwarded hop by hop, and they install a state on every hop as they go to go the other direction. And in non-storing, they only install a state in the root, no state in the intermediate node. It's a unique as packet from the child to the root, indicating which its parents are. And now, if the root has all the child to parent relationship, it can build a source route path to the devices. Okay, those are the main modes of the traditional Ripple. As I said, there is an AODV Ripple, which is the extreme stateless thing, which will not install routes proactively. And I'm not discussing that today, no time, and it's really a different world. But there is, on the other extreme, for automation type of application, when you really want to have an optimized path and very specific constraint, there is the new concept of DAO projection, which is being standardized now at ROLL, which is the working group where Ripple is being defined. So DAO projection is how you do centralized Ripple, how you have an external controller which can be collocated with the root, or for which the root just appears as a front end. That will compute the best path for a certain A to B for a certain flow. The two things that will be done by DAO projection are, in the first place, one thing you could want to do is compress the SRH. Sorry for the typo on this slide, the source route header. Because I showed you the overhead, you have all the hops, all the intermediate hops, and it's a strict thing. Now you could say, hey, I want it loose. I don't want all those hops in my routing header. I want it loose, but I still want to maintain the security properties that I had with RH3. And so what the controller will do is it will build storing mode segments along selected path in the DAG that the root uses a lot with SRH. And because now you have intermediate hops in memory in the RIB, you don't have to place those hops in every packet. So you can make the source route header loose as opposed to strict. Traditional Ripple is strict, you have all the hops one by one. With a segment which is installed as a DAO projection route along a certain path, the steps for which you have installed the path can be elided from the SRH. So the SRH now is smaller. So that's the first thing you can do with DAO projection. The second thing you can do with DAO projection is to establish a new DAG inside the DAG as an overlay. It's basically what we call east-west routing. So as opposed to the first one, which was just optimizing the path along the normal Ripple DAG, making the SRH smaller, a track, as we call it, which is really this overlaid DAG, a track will enable optimized east-west inside the DAG. So as opposed to going through the common parent, now you will establish a path via intermediate hops in a more direct fashion. And basically the way we do that is typically that the main DAG is operated as non-storing. That's what most people do in IoT. So you operate the main DAG in non-storing. You compress some hops with segments, so the segments are allow a loose source routing header. Well, same thing for the tracks. The tracks will be Ripple DAGs using a loose sequence of hops, and there will be segments to interconnect this loose this structure, this skeleton, if you like, to complete to connect the dots. There will be segments as well in the tracks. So the track is another DAG overlaid on the main DAG for just one A to B pair for the most piece. And the track can have multiple paths, and segments will join the dots in this loose path. So let's see an example of what I said first, because maybe it's better with the drawing. So let's say this is a classical ripple DAG, right? And I just showed the preferred parent tree. And here is the path again between the root and Mr. 56. And like I said earlier, you've got all those hops that you have to indicate on every damn packet. So if you have a lot of traffic, then you have 4 IP addresses, 13, 24, 35, etc., that you have to copy on every packet to insert. And that makes your packets longer. And because they are longer, there are more chances that there is something that causes a loss, basically something that interferes in the middle of the transmission and causes the loss of the whole packet. Smaller packets have better chances to go through. They will have less latency, they will use less spectrum. So we want to compress this. So what the root will do to install what I call the segment is it will send a DAO, which we call a projected DAO, because it's projected by the root all the way to node 46 in this case. So it's like, send it over the network as a unicast. And it's basically a DAO which says, hey, advertise this along that path. So the path of the hops of the segments are serial, they are hop by hop, they are strict, and they have to be indicated in the PDAO, in the storing mode PDAO. And the storing mode PDAO will basically follow all those hops one by one and install a state towards 46 to go to 56. So let's see how that happens. So the DAO has reached 46. The DAO includes the hops in the segment, in this case 24 to 35, 46. That's what you want to compress. That's what you don't want to see on every damn packet. 46 sends it to its parent in that list, so that's 35, and 35 forwards it to its parent in the list. Each time they remember, oh, from the guy who passed it to me, I have a route to 46, which is what we call the target of this DAO. And once you reach the first in the list, which in this case is 24, because we just wanted to compress 24, 35, 46, basically 24 sends a unicast DAO, projected DAO to the root. And with this, the root knows that the path was installed toward 56, I'm sorry, in 24, in 35, and in 46. So they all know how to reach 56. You don't need to give them the full source route path. Okay, this basically summarizes what I just said. And now there are two consequences for this. The first consequence is if there is a packet from 55, which is again sent along the default route, when this packet hits 35, because 35 now has a storing mode state, even if the whole DAG is non-storing, right? There is now a little islands of storing in the middle of the non-storing. And in particular, 35 knows how to go to 56. So we end up with the storing mode behavior that the packet goes to the common parent and down, only for the nodes for which there is a PDAO, which is on path of the packet. So in this case, 56 is on path, 35 is on path of the packet from 55 to 56. 35 has a PDAO state, which is equivalent to a storing mode state. So it will effectively forward down, and 46 has this connected route state, so the packet can flow. The first consequence of what we just did is now we can avoid the overhead of path, the stretch of going all the way to the root for all traffic. So if the root is very clever in placing some routes like this to special destination where the sources are nearby, it just places the path at the common parent and down, and then the packets will avoid going all the way to the root. The second and most important consequence is the path from 24 to 46 to go to 56 can now be elided in the source route. So basically the source route can say 13, 24, 56, and not the nodes in between, which basically is what you can see here. And so 13 doesn't have a state because it's still not in the DAO. So we need to tell 13 that we have to go to 24. But then 24 all the way down is elided. And so 35 and 46 are elided. Effectively, we are seeing the packet as it is when it arrives to 46. But if it was as the way the routing header games play, there is a swap of addresses which happens. So 13 initially was the destination when it was the first hop, but then it has been swapped and placed in the routing header. Anyway, so that's details of routing header operation. Now, if you look at this from a longer distance, and I don't want you to digest this picture right now, there's a lot too much information there. But what it's telling you is with the DAO projection non-storing mode, we can build what we call a track, which is an overlay inside the main DAG between an egress I on the left and an egress E on the right for what we call east-west traffic. And so the track definition, if you like, will give some dots on how you can get from I to E. And in this case, you have basically two of those dots, which are relay A and relay B. Now, it doesn't mean that all the packets will go from I to A and A to B and B to E. Effectively, they won't, because there are hops in the middle. For the hops in the middle, we'll use the PDAO as before, but inside that track as opposed to inside the main DAG. So what you've seen before, now imagine that ingress is the root of this little DAG that we talk about here, this little overlay. Well, we will install a segment using storing mode, starting at G, F, and ending at A. And that's how A, when it gets a packet towards I, can know how to forward to E. So the source route header will say, I'm going to A, I'm going to E, I'm delivering to a target. And F and J are ignored because there is a storing mode PDAO segment, which is installed between the two. Another segment can be installed, for instance, between I and B. And even worse, that can be yet another overlay, which I represent as this tunnel, which is yet another track, which could allow A to talk to B. So I could have now two solutions to get towards the target. It could say, hey, either I use the segment F and J, or I encapsulate into this additional track to get to B. As long as you use a segment, you don't need to re-encapsulate, you stay in the same instance. If you use another track to go between nodes, then you have to encapsulate. Each time you place the packet in the overlay, you encapsulate. The track is an overlay. Now all the details are on this slide, but you have to digest it on your own. And then this is all the explanation about the way the encapsulation works. And then again, I will ask you to digest it on your own. There's a lot to be understood to figure out how it works. But the bottom line is you can build a number of profiles. This is the simplest profile where we, as I said in case one, we just take the main DAG where our root is on the left, and we compress some hops using segments. And you see segment 1 and segment 2, two different DAOs, and you see where they arrive and when the DAO ACK is sent back. So for instance, the segment 1 is PDAO 1 arriving from the root at E, E passes to D, D passes to C, C sends the ACK. Now there is second PDAO, storing mode PDAO, which goes to B, indicates that A is the previous hop and then sends the ACK. And if you look at what the targets are, now you can figure out how the routing table is built. Basically, the second PDAO says if you want to reach B or C, you need to pass via A and B. And so A will install a state via B to get to B and C. That's what's going to happen. And now you've got all different sorts of mode when instead of having a segment, you have a track, as I told you, with the vertical tunnel that we saw. To get from nodes, you can effectively re-encapsulate to another track. The track can be implicit if you just lay out a segment with a track ID, which is not the main DAG. It can be implicit, but then it's just a one segment track. or it has to be explicit, in which case you first install the track and then you install all the segments. Oops, sorry, I'm not pressing the right button. Oops, I don't know what happened. I need to go back to the slide I was. Okay, so I'm explaining all the different modes in those profiles that you can find, but think that you can go all the way to building very complex structures which nest track into track for east-west. But really, that's not what's going to happen. What's going to happen is you will build something which looks very much like this. You will build a complex path, a complex track, as we call it, between ingress and egress. By complex, we mean that it's not the serial sequence of A to B to C, because the serial sequence will always break. There will always be some links flapping. If you have only one way to go from I to E, it's going to break. So you need the relay nodes A and B to have one or more than one solutions. If one path doesn't seem to work well at this time, they need another path. And how to use that wisely is the purpose of the new raw RAW working group at the IETF. So then again, on your own, I hope that you will go through those profiles. And now we are reaching conclusion time. So conclusion is RPL has a number of functionality which are new and unique in the routing world to adapt to the problems of IoT. And because of the links and the quality that can be measured different ways depending on what you want to optimize, it has objective function which allows an instantiation of the base routing protocol for the needs of the day. It does anisotropic routing, which basically allows to only optimize the path towards the root and minimize topological awareness that you're having at that time. The same graph is used for going towards the root and going back from the root. So once you have selected nodes as parents, there will be also the nodes which give you the traffic back from the root. I told you that the maintenance of the path is reactive. That's how we avoid spending all our energy on paths that are not being used. That's another thing that is being done by this RPI. We basically have flags that detect that when the topology is inconsistent. We have trickle, which allows to minimize the amount of repeat of the same information that happens regardless of the density of the network. Will get pretty much the same amount of broadcast. That's a very, very important concept when you density augments. Because we build DAGs, we have non-equal cost multipath forwarding. Most routing protocol, they do a tree or they do equal cost multipath. But here, because of the DV nature of RPL, we can do non-equal cost multipath. We basically select different parents, and the cost for those parents it can be different. The cost being the rank, basically. Because we have multiple instances, we can effectively we have multiple topologies. You indicate the topology in the RPI in this by hop header, and the topology is pre-installed, it's proactive before it's being used. And last but not least, RPL is the routing protocol of choice for ANIMA, which does autonomic networking. And that's because RPL basically, when it spreads from the root, it also spreads its own configuration. So the node, when they join that instance, initially they just know that they should join that instance 5, but they don't really know how it's operated. They will find the information in the DIO itself. So a lot of the parameters for the routing protocols, instead of being configured in every node, they are learned from the protocol as the DIO spreads from the root. And that's pretty much it. So thank you all for the time spent on this. I'm a few minutes late. I don't know, Nalini, if we take questions.
Sure. Yeah. If anybody has questions, please go ahead. I know we're a little bit late, but there's people who are staying, and I'm certainly willing to stay if you are. And so if you guys have questions, then please either put them in the chat window or raise your hand, and I can unmute you. And I'll go ahead and start off. So maybe I'm misunderstanding, and I need to think about this some more. I've been working a lot with MLS and binary and ratchet trees, and it occurs to me that since this is not a mesh network, it does seem to me that it is in some ways more like a binary tree. And the reason I bring that up is that if it's a binary tree, then the source routing and a lot of that stuff, the routing is there by definition. And then also the sibling is there, a sibling and parents. I mean, all of it can very easily be calculated by definition, because that's how binary trees work. Do I have a fundamental understanding?
Yeah, you're basically, there are two things where RPL departs from that description. The first thing is, effectively, we are building directly acyclic graphs as opposed to binary trees, right? So
right.
when a node sees this DIO message coming from the root that has been repeated by the guys nearer the root, it will see the cost from the guys who repeat, that's distance vector for you, the cost from those guys to the root. And it will select not just one, but several of them. And there are constraints not to be greedy, but it will select several of them. And now it can forward packets toward the root via any of them. They are called feasible successors in AODV. So it's not a binary tree. That's the first thing. Second thing is, in the wider world where everything is stable, you could effectively be building a binary tree, like, for instance, on Ethernet, there is the spanning tree or something. But it's in the radio world, those links flap all the time. So the nodes keep changing the parents that they select. They could not present how that works, but basically, as long as you have a feasible successor, you don't have to change your rank, and you can appear as stable to your children. But at some point, you might lose all the feasible successors because all the links are down, and you have to reparent somewhere deeper than you are. And that's when you effectively have to go through one of the RPL procedures called local repair and global repair. But basically, you don't have a stable tree as you might think about it. You keep the whole topology keeps changing, and at some point you might be sending a packet which flies over towards the root, and the path down towards your destination is changing at this very moment. And maybe by the time the packet goes down, this has been fixed.
Yeah, I see what you're saying. Yeah. No, that's yeah, because I think it was just you gave examples
but you cannot see it as something which is very stable.
Yeah, there's a point at which it becomes more of a mesh, and it's I see your point about stability, and that it leads. There's a couple of other questions which have come in based on this, I think, and I mean I'm sure other things too. So I assume that the trees, like in your examples, you gave balanced trees, but that's not necessarily true. And it seems like there's a point at which it becomes almost a mesh, but up closer to the root. Would that be correct?
Well, I mean, yes, a RPL is designed for routing inside a mesh, if you like. That's but it's what RPL builds. The mesh is the first picture I had everything blue, right? My radio connectivity, and then RPL will paint that mesh with one or more topologies, with one or more optimization, each topology being a direct acyclic graph, or even a collection of direct acyclic graph. Well, so each instance is basically defining a topology, and that topology is optimized for a certain result. And so the routing towards the root always follows the topology. It's regardless of the mode. But what changes is when you go down. When you go down in non-storing mode, it's the root which knows all the vertices of the selected topology, so the subset of all the possible links, if you like, which have been selected. And they are selected because each top selects one of several preferred parents. I'm sorry, I'm getting a call. I have to let it ring. Okay, so sorry for this. So I was saying that the path back is seen in memory as a graph. Effectively, you can create a mesh, but only the vertices that are selected by the nodes as their parents are there. And so if you have an arrow in memory of the root, which goes the other way of, so basically parent to child relationship, by inversing the DAO says, I'm this child, and I have those possible parents. So I could go to the root via A, B, or C. Well, the root will reverse that and say, oh, to go to this particular child, I can use A, B, or C. How do I get to A, B, or C? Same question again, use this parent. And so recursively, the root can compute a path out of many possible paths with the topology that it has in memory, along the reverse DAG, if you like, from the root to the device. So if you remember this concept of fan-out DAG, which is all the possible paths that the device could use to go to the root, which is basically the path that storing mode DAOs would follow. It's also when you reverse it, it's the path that the data packet can follow. It's this aggregate of path. A path is really the experience of one packet. The DAG is the collection of possible experiences for a collection of packets. The DAG is a potential. A path is an actuation. It's one that what a given packet that you have placed in the network has experienced. So RPL builds potential, and the forwarding decides what the instance will be. In the case of non-storing, that decision is made by the root and indicating the source route header.
So, no, great. You know, that again, that leads to yet another question. Are there studies of like the reconfiguration costs in case of failure? The question is the use of unique logical paths or your source route header. I mean, there's a risk of failure as well as being a focus of overload. Yeah.
What can I say? I can't point to an explicit paper. What you figure is a radio link never works forever, right? And if you wait for something to go down, even on a single hop, you may have very disappointing results. Now, when it's multi-hop, you multiply those effects. That's why it was a requirement from day zero. It was not even a question. It was a requirement coming from the users, effectively, for which we defined the protocol, that the protocol would define multipath solution. So that's why the protocol defined DAGs. Now, when you want a tree, the preferred parent tree is still a tree. So we use it for multicast. RPL basically can flood the preferred parent tree for a multicast address. So basically, you inject the multicast address at several points on the same DAG. You use storing mode. And so all the parents of all these points are aware and know which children need the information. You build a preferred parent tree and you distribute the multicast over it. So that's part of RPL. That's section 12 of RFC 6550. But you never want this only a tree. On wire, that's typically what you do. But even in DetNet, you want more than one path, actually. Even on wire, when you really want very good reliability, and possibly when you want to survive breakages, not only interferences, but breakages, you need multipath. And so DAG is a multipath structure.
No, for sure, because that's for sure. I was thinking is that, you know, if you're the root compromise and failure, as I say, we can talk forever. What I'd love to see, I know, Rahul is going to show traces, because now I really want to see traces, packet traces from some of this stuff. And I'm going to talk to Rahul because I know that's something that we're adding another session, another 2 or 3 sessions to this whole series. And one of them is going to be Rahul going over traces, because in particular, I've done OSPF traces, and so I know the multicast, the multicast groups that for OSPF. But it'd be very interesting to see what happens with this. But
the big difference is OSPF is link state, meaning that you flood LSAs.
Yeah.
So that's why you have multicast group, but think thousands of nodes. You don't want to flood thousands of nodes on constantly links, right? So the concept of flooding just doesn't work. Now distance vectors are different. What they say is I'm this node and I am this far from the destination, blah. In RPL, we use it for only one destination, and that's it. It's the root. So basically, as the DIO spreads, nodes know how far they are from the root. And any node that they see which is closer to the root than they are is a feasible successor. That's how you build a DAG. But when you repeat the DIO, you change it. You first process your parents' DIOs, you figure out which is the preferred parent, which other parents are feasible, you compute your own rank, and now you can send the DIO. So many fields in the DIO are repeated, are propagated as is, but things like the distance is changed. So you see the difference between that and OSPF. OSPF, you flood the LSA throughout the network. Everybody gets the same copy as fast as he can. Here, in DV, you understand the distance of your parents. You select the best ones. You select feasible successors, and now you can propagate the information. You can propagate the DIO with your own distance in it. And the distance in this case is called the rank. So that's what you will see in those trays, that the DIO is kind of repeated, but with changes because you need to put your own rank. Now you will see. Yeah, go ahead.
Yeah. It sounds unicast, using very little multicast. Sorry to interrupt you.
There is no flooding across the network, but
right.
The DIO is a one-hop broadcast, meaning that everybody in my range will get it. And you know, the radio, I mean, when you send something, everybody in range gets it anyway. So the concept of unicast is, unless you use very directional antennas, it doesn't really play. So in the IoT, everything you send is a MAC layer broadcast. It's a one-hop broadcast anyway. It's everybody on your wire will get it. So, and nobody can transmit, just like a good old yellow wire. So basically, sending a DIO as a broadcast one hop doesn't cost more than sending it as unicast. It's just consuming the spectrum. But all the guys who are in range will read it, and they will see that presents a better feasible successor to go to the root, and that's how they can reparent. You can always reparent to somebody as good or better, but you cannot reparent somebody who's deeper than you are, because that may create a loop. He might choose you again. That's what distance vectors are about, right? You can never reparent somebody deeper than you are, unless you do some precaution. And that's the thing that Triple explained, how you take those precautions. Once you lost all your feasible successors, how can you reparent deeper without creating a loop?
Yeah. Go ahead. Sorry, I get all excited.
Yep.
Okay, so this is very, very interesting and exciting. We're way over time, but thank you so much, and I really look forward to talking to you more at IETF in Philadelphia. I encourage everybody
to go. I won't be in Philadelphia, Nalini. Sorry for that. I cannot fly this time.
Oh dear. Oh, I'm sorry.
Yeah. Tell my boss, but yeah, I'm not flying.
Okay. Maybe then London in November. But thank you so much, Pascal. You're doing the next one as well. That is coming up in 2 weeks. And then, as I say, we're going to have we've added a few more to this session, and a bunch of them have to do with trace reading of a lot of the concepts that we've seen. Because I know definitely for me, if I can see it in the packet, it really helps me to understand what's going on. But Pascal, I love the way you explain things. Great session. And, shockingly enough, I feel like I may be starting to understand some of this. So thank you so much.
Because it was very, very dense for an hour. I mean, all those things I could say and all the things I could not say, it was very hard.
No, it is. It's there's a lot of very new concepts. That's why I said a lot of new concepts. But this is great. Yeah, and thank you guys so much, all of you, for doing this. And thank you to everybody who's still there. Any more questions? And I'll forward them to Pascal. And Pascal, thank you again. And so I'm going to go ahead and end the webinar now. Thank you.